And I'm back. They tried to get me last Thursday. Well, I figured it out. They can't keep me out. Okay. And I even figured out how to share my screen on my wife's computer. Okay, so we were just discussing calcium metabolism. Here's kind of the bottom line over here. So make sure you know this. There are 3 things that decrease calcium and 2 that increase them. To decrease, you're going to need energy, right? Because you're going against a big gradient. So it's going to be an ATPase or your sodium calcium exchanger over here. So this is plasma membrane calcium ATPase, sodium calcium exchanger. And then in terms of your smooth ER, you've got your Circa over here. We've talked about Circa before. To increase calcium in the cell, and this is like, cells stimulated to do something. IP3 binds to its IP3 receptor on the smooth ER that releases calcium, or calcium-induced calcium release with the ryanodine receptor. Okay, questions about that? Comments? Okay. Oh, you people all seem really smart. Okay, so next thing to talk about is how transporters are used to help your red blood cells transport oxygen. And it has to do with pH to a certain extent, not totally, but to a certain extent. Hemoglobin's extremely good at transporting oxygen. It's really good at picking up oxygen at high oxygen tension and releasing it at low oxygen tension. Each hemoglobin molecule will bind 4 oxygens, and it's a cooperative thing. So at high oxygen concentration, they bind really, really well, and they grab onto it and they stick to it really well. At low oxygen, one comes off, and that makes the next one, and then the next one, and the next one come off easier. So it's cooperative binding. So that gives you a really, really steep curve in terms of low oxygen. It really doesn't bind well. High oxygen, it binds fantastic. So that makes it a really good oxygen transporter. In fact, there are no artificial bloods. People have been trying to make an artificial blood, since the 70s or 60s or something. They still don't have anything good. Wouldn't it be great to have a non-biodegradable blood substitute? You're in a war situation, some guy's bleeding out. All you got to do is pull it out of your pack and put it in his body, because you don't have to store it at cold temperatures. Well, we don't have one because hemoglobin's so goddamn good at what it does. Another thing that helps this to happen is hemoglobin's binding of oxygen is pH sensitive. So in your tissues, you're making a lot of carbon dioxide, and carbon dioxide will combine with water to form carbonic acid and then diffuse into hydrogen ion and carbonate. So in your tissues, you've got a lot of hydrogen ion around, and this carbonate is how most of your CO2 is going to go to your blood. So out in the tissues, you've got this enzyme, carbonic anhydrase, that's converting your CO2 into bicarbonate and hydrogen ion. Bicarbonate, again, will be transported by the blood out to the lungs, and in the lungs, it'll go in the opposite direction. So this enzyme is reversible, so it'll take bicarbonate, combine it with hydrogen ion, and you'll blow off CO2. So out in the lungs, as you're losing CO2, you're also losing hydrogen. So the lungs are very basic and the tissues are very acidic. Okay. So your hemoglobin then, when you're in the tissues at acidic concentration, it can release a lot more oxygen than it would if there wasn't this pH mechanism. So the difference between here and here is extra oxygen that's being released because the solution is acidic. Over here in the lungs, it's picking up this much more oxygen because it's basic in the lungs. And basically, you change the pH inside that red blood cell, the hemoglobin is going to bind hydrogen ions, and it's going to change shape a little bit, change conformation, and bind oxygen better or worse. So out here at the tissues, you're releasing. So you can imagine if there wasn't anything like this, your oxygen level change would be from here to here. Now it's from here to here. Okay, big changes. So how do your blood cells do that? I'm glad you asked. So in the tissues, you've got a lot of CO2 around. CO2 simply diffuses through the membrane because it's small and nonpolar, comes into the cell. Carbonic anhydrase then converts it into hydrogen ion and bicarbonate. And you've got this chloride bicarbonate antiporter that then transports that bicarbonate out. So you're leaving hydrogen ion behind, and it is acidifying the inside of the red blood cell, helping the red blood cell offload oxygen in the tissues. And so this is our chloride bicarbonate antiporter. Nice thing about this antiporter is that you've got a negative charge coming in, negative charge coming out, so it's electrically neutral. It's not going to be slowed down by any membrane potential. So this is, and what it's doing here is keeping this equation moving in this direction, right? Le Chatelier's principle. If you lose the product, more reactant will react and you'll get more of it, all right? So it's keeping this thing going in this direction. Now, this bicarbonate is in the blood, and now the bicarbonate and the red blood cells make their way back to the lungs, and now you've got a lot of bicarbonate, and CO2 is being lost because you're breathing it out, right? CO2 in your blood is higher than it is in the atmosphere, so it leaves this way, and that pulls the equation in this direction. And so now bicarbonate's coming in, chloride's going out, and the pH is now going up inside the red blood cell, and that's allowing it to bind more oxygen. So this mechanism then is helping the hemoglobin to transport oxygen a lot better. Again, in the tissues, it's offloading oxygen because it gets acidic inside the cell, and in the lungs, it's onloading oxygen because it's getting basic inside the cell. And this bicarbonate chloride antiporter is helping that to happen, helping to keep it one directional. Okay, another thing that transporters are used for are in lymphocytes. So look at this lymphocyte. This is a lymphocyte you put into a hypotonic solution, right? So this is normal. It's at 0 times 0. And then you can see it swell up, get bigger and bigger. And hypotonic solution, water is going to go in to dilute the internal solute until it's equal on both sides of the membrane, and it swells up. Now, if you watch these lymphocytes over 20 minutes, though, it's going to go back down to normal size. You haven't changed the external tonicity. Okay, it's still the same hypotonic solution, but now it's back to a normal size. And here you can see the time frame here swells up pretty quickly because of that hypotonic solution, and then over time it goes back down to its normal size. Why is that? So let's talk about osmosis really quick. So I don't know if people really get confused by this. You get hit by it, I think, in every course in every semester. But the bottom line to osmosis is this. Water is always going to move to equalize the solute concentration on either side of the membrane. So here, if you've got a semi-permeable membrane here, you've got more solute here than there, then water is going to go over here until it dilutes this solute to the point where it's equal on either side. That's your osmotic pressure. It's always going to go towards the area with more solute. In a cell, if you put a cell in a hypertonic solution, water is going to come out until the osmotic strength inside the cell equals outside. So it's going to shrink down. Plasmolysis, I think it's called, shrivels up. If you put it in a hypotonic solution, it will swell up until it's with the solution it's in. If you put it in a hypotonic solution that's too hypotonic, the cell membrane will get stretched too far, it'll rupture, and then the cell will explode. Get that sound again. Okay. So what happens with a lymphocyte is, here we're going to put it in a hypertonic solution, 450 milliosmol outside, 300 millimol osmol inside. When you do that, water's going to rush out to concentrate it. The cell's going to shrivel down. Now, over time, it's going to transport hydrogen ion out and bicarbonate ion out in exchange for chloride ion and sodium ion, okay? So sodium coming in, chloride coming in, solute coming in. So your sodium chloride is increasing inside the cell. Now, if that's all that happened, you'd be changing one solute for another solute. It wouldn't change a whole lot, right? But because of this equation we talked about before, CO2 diffuses into the cell, carbonic anhydrase makes carbonic acid that dissociates into hydrogen ion and bicarbonate ion, and these get pushed out. So you've got this equation going in this direction, which is replacing these as they leave, and you've got sodium and chloride coming in. So the net change here is sodium and chloride coming in. When solute comes in, water comes in too. So we started out in a hypertonic solution, and we transport sodium in, and eventually what we end up with, and we put it in a hypotonic solution, the cell shrinks down until it's 450 on either side. Okay, so now it's equal. And now it's going to put sodium and chloride into the cell. And when that happens, water will go in with it. Now it's going to swell up again back to normal size. The difference is it will now be 450. Oh, come on. Now it'll be 450 inside, okay? So it will equalize, it will get back to a normal size. The tonicity is different inside the cell than normal, but apparently it can deal with that better than change in cell size. So this is how a lymphocyte will regulate its size based on the tonicity of the solution outside. And again, it's like these lymphocytes are disease fighters, right? If you've got an area of infection, lymphocytes will chemotactically crawl into that area, cell crawling, and try and fight that infection. So an area of infection might be hypotonic, might be hypertonic. The cell needs to stay a certain size in order to be most effective. And so it's able to regulate its cell size, okay? That's the lymphocyte. And in the notes, I talked about this, what's in this figure here. Didn't have time to draw the opposite figure, but basically, if you put this in, if you now take this guy, like this, I'm like magic. Hey, Mr. PowerPoint. Bum, 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 bum. They call him Dr. Slash. Oops. Oh, come on. Yes. Somebody's chatting me. Okay, so now we take this lymphocyte that just got used to 450 milliosmol. We put it back in what should be isotonic, but now compared to what it's used to, it's now hypotonic, right? So water is going to come in to dilute that to 300. The cell is going to swell up. Again, the cell doesn't want to be this huge size. So what does it do? It reverses these transporters. Now chloride's going out for bicarbonate in, sodium out for hydrogen in. The extra hydrogen and bicarbonate are being converted back into CO2 and leaving the cell. So everything just reverses when you go in the opposite direction. Let's see what the chat's about. If I never have to do acid-base calculations again, it will be too soon. Oh, don't say that, Christy. Acid-base, I love it. Henderson Hasselbach, come on.
Okay. No, they're not fun.
They're fun when you know them and other people don't. You can lord it over them. That's kind of where I am. All right. Hey, you're not muted. So I don't have much more to talk about. One more thing to talk about. And that is the salivary gland. So your salivary gland is really important to your tooth health, if you didn't know that. Saliva is basic. Usually things that are going to break down your teeth are bacteria. They're secreting acid. The acid's breaking down the enamel on your teeth, and that's how you get tooth decay. That's what starts tooth decay anyway. What your saliva is doing, I've got a lot right now. It's coming out. It's coming out. What your saliva is doing is neutralizing acid in your mouth. So your mouth should be a little bit on the basic side because the saliva is doing that. This is a salivary gland. And I can say that because I searched Google for salivary gland and this is what came up. I'm not an anatomist. And here's what's going on in the cells of your salivary gland. So the question is, how do you get potassium and bicarbonate into that saliva to go out to your teeth? So there's an awful lot of transporters it takes to make that happen. You don't have a potassium bicarbonate co-transporter. It doesn't happen. So where does all this come from? Number one, our good old friend, the chloride bicarbonate co-transporter. Okay, chloride coming in, bicarbonate coming in, going out. We've taken care of the bicarbonate just like that. And that chloride then can be balanced by allowing chloride back out of the cell over here. And then how do we get potassium out? Well, we're going to use the same thing we used in the lymphocyte volume regulation, sodium coming in for hydrogen going out. Now we want to exchange this hydrogen for a potassium. We've got the hydrogen potassium antiporters. Potassium goes out. Now we've got potassium bicarbonate outside. And now we need to balance the sodium that's coming in, right? This hydrogen is balanced. It's going out and coming back in. We need to balance the sodium coming in, the potassium loss. And we've got our good old friend, the sodium potassium ATPase over here, pumping that sodium back out, pumping potassium in, and this allows this whole mechanism to happen. So again, think about balancing ions. We want to lose bicarbonate and potassium. How do we do that? Bicarbonate is easy, just the chloride bicarbonate antiporter. We need 2 antiporters to get this potassium out because we don't have a sodium potassium antiporter. Sodium comes in for hydrogen, and then the hydrogen comes in for potassium. Bum, 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 bum. And that, my friends, is chapter 8. So when you're studying chapter 8, things to keep in mind. Energy, right? Is it passive or is it active? If it's passive, it's either simple, just through the membrane, or facilitated, and facilitated transporters can be reversed. Remember, this chloride transporter is facilitated, this is facilitated, this is facilitated. These could all go in either direction. And then active, you've got pumps, 4 different types of pumps, and they're always going to be producing a concentration gradient and using ATP. And then you've got co-transporters like the sodium potassium antiporter or the sodium glucose co-transporter, symporter. You also have a sodium amino acid symporter that brings amino acids back into your body. So those are the mechanisms. The mechani. Latin, that's Latin. Plural of mechanism, mechani. Okay, questions? Comments? Discussion? Are we all good for today? Okay, we'll meet you back here Thursday. I'm not even sure when your exam is. It must be about 2 weeks from now. I'll see if I can find out before that comes. Later, guys. Have a great day.